Our first speaker is Oscar Antommattei, and Oscar is a chief concrete engineer and material engineer manager on Kiewit Corporation. He leads Kiewit engineering technical services for concrete from the design and the production point of view. He started his career 22 years ago and is working with a concrete producer and general contractor. He joined Kiewit in 2012, and he also worked in the design of forensic investigations with an engineering consultant. Oscar is a fellow of ACI. He also served as a member of the board of director of Technical Service Committee TAC, ACI Foundation Concrete Innovation Council, and a variety of other technical committees. He also served in ASTM, ACE, and other entities. In 2019, he was recognized as the most influential people in the concrete industry in the United States, and he holds a bachelor and master degree in civil engineer, and he also has a PE in different multiple states. Welcome to Oscar.
And something that Julissa didn't say, she and I went to school in Puerto Rico together, so she's a good friend of mine for over 23, 25 years, so good to be here with her always. Let's see if I'm clicking the right thing. There we go. So we're going to talk about North American standards, and I always like to brainstorm a little bit here this session with perspective. Perspective is extremely important when we talk about standards and requirements. And I use this project I found very interesting. It's actually from Colorado Springs. Anybody that doesn't know, Colorado Springs is south of Denver, about an hour, 15 minutes from Denver. And that's the U.S. Olympic Museum. So if you go to Colorado Springs, the U.S. Olympic Museum is there. It's going to be on the right of that nice bridge. And that's a pedestrian bridge. We had to build the pedestrian bridge. And we were in charge of, obviously, the concrete requirements across the project. We were not to build the museum, but actually the bridge and site work. And I put a lot of question marks around, because it started making you think, what type of concrete I need everywhere? What type of exposure conditions you have everywhere? What type of construction demands you're going to have to actually make sure that you build the concrete to a quality of work that is acceptable to perform in service, right? So when you think about it, you have the abutment and the substructures on the bridge. You have the superstructure on the bridge, which is an architectural high-performance concrete. You have obviously the concrete inside of the building. You have the site concrete, which is around the building, and you have all the streets around the site. And you think about it, not all of them are going to have the same mixes, the same construction demands, the same finish quality, the same in-service conditions. And that's extremely important to understand concrete, because without knowing or having the perspective of each piece of concrete everywhere on site, you cannot understand it. So when you take a core and you look at it, all of them are going to look a little bit different. And there's nothing wrong with that, because there's a need to make them different. So start kind of opening a little bit your head to look at perspective and differences. And that's extremely important for North America, because when you think about it, even in USA, we're going to have 50 different ways at least to do something. We have 50 states. And if you go through Mexico, USA, and Canada, there's going to be different ways of doing concrete in Mexico, USA, and Canada. And that happens with standards. But what we commonly have is a challenge with the specifications. What is the main challenge with the specifications when you think about it? People want to prescribe things because they believe that based on their experience, they need to have certain type of requirements, and they're trying to now force the user to follow those requirements, because that's the belief, right? That's what the engineer believes needs to be done to achieve quality concrete. But then there's also another approach of being looking more about the performance. It's not what I think, they need to do, but actually what are the conditions of work that that person needs to understand to make the right selection of materials to be used in that location. And if you think about it, everybody agrees that those are the two types of approaches that you have around, right? And you can see that, and you're going to see in a minute here, that in USA, we take a look at different things. We took a look at things very different than Mexico and USA, right? And you also expect that, okay? One example I have here, I believe is very interesting, and I call it clear goals and undefined requirements. And if you read it, everybody will understand that those are very clear goals. We want that, right? But think about putting that in a spec. What are you going to do with that spec? Nothing, because you don't have a way to measure. There's no metrics. What is low permeability? What is low permeability to me is different than what is low permeability to you. What is dimensional stability and freedom from cracking? What is that? Right? Is that a certain shrinkage value or that's cracking? Because you're going to get cracking for many different reasons, right? So it's important to have clear goals but defined requirements. Now, the other problem we have is the bottom one. Hidden goals and defined requirements. So now you have all of a sudden a prescriptive approach to a specification. And they say, well, I know I don't want to have a lot of shrinkage in the mix, so I'm going to force them to do something. I'm going to force them to have a certain amount of rock, or a certain volume of paste, or a certain... But you're not thinking that they need to have different demands of construction for different applications, and you need to make sure now that all of a sudden the material is workable, strong, and durable, as you also have prescriptions, right? What I also say in a simple term, when I don't want to get too technical, I say if you do exercise and you do marathon running, you want to run a marathon, 26 miles, and you're going to go with your shirt comfortable, with your shoes comfortable, and you're going to go ready for the race. You're going to do well. You're going to do well. You're going to perform. But then if you go and say, I'm going to do another race, and I'm going to do it the way somebody tells you to do, and you're going to put dress shoes, jeans, a backpack, you're not going to hydrate yourself, you're now forced to do something, so now your performance is going to decrease, right? Same thing happens in construction. Performance is all about what you need to do to build the work, and obviously make a performing service. So the other fundamental part that I want to mention is, what about smart requirements? And now you may be turning your head around and thinking, where the heck did I see that before in ACI? Or where did I learn this in engineering college? Well, you never learn all this in engineering college when we were talking about science and engineering. Now, if you have been through corporation trainings and knowing how to develop goals, is the approach, the smart approach to setting goals is a very important fundamental of setting a goal. Why is that? Because it's specific, it's measurable, achievable, relevant, and time-bound. What does that mean? That there's a performance criteria that you're going to meet, you're going to be able to measure, you're going to be able to start and finish. Simple. So the question is, why our specs are not smart? Right? If you want to be constructible, high quality, you need to have a spec that is smart, that is specific, that you can measure, that it can be achieved, that is relevant to the performance of the work, and that you're going to be able to complete, right? Within a certain time, right? Pretty simple, right? So, anyhow, very easy concept to understand. So then let's go to the technical side of things, right? We need to make sure concrete is what? Strong, durable, workable, and economical, right? And my approach to economical is very different to what many people think is economical, okay? It's not having a low unit price of your concrete. That's not what economics means. Because you can have a lower cost concrete that actually takes a lot of time to be built and costs a lot of money to the contractor to get it done because it's not a good mix. Now you can have a little bit of a more expensive concrete material that actually is easy to build, is going to perform well, is going to be constructible, is going to be achieving all the properties you want, and you don't have to revisit again. So cost relates to also performance in construction, performance in design, and obviously there's a unit price related cost there too. Now, let's start talking about North America. So I started using all these snapshots of different standards to compare. Okay, so I'm going to use the main concepts of, everybody know what slump is. Everybody knows, like it or not. There's different reasons why we do it, why we still do it, but there's not very much technical rationale to do it. But we still do it, and everybody's easy to understand. So I'm going to start with the slump. So one of the things that, this is an excerpt from, I'm sorry, this is not slump, this is mixed design proportions, I apologize. The mixed design proportions in this case, in ACI 301, when you read it, it says concrete mixture proportion and characteristics indicate the proposed ranges of mixture proportion and changes in the materials and all that. So you know what? In the United States, we are required to provide mixed design proportions. The actual formulation of your mixes is a requirement for construction. It's something very commonly done. But what I'm showing here is that actually in Mexico and Canada, that's not the case. You start asking why, right? Start thinking about how we do things, how much we love to prescribe things in the specifications, but the concrete producer is responsible for that formulation. And the concrete producer is supposed to work with the contractor to find a mix that actually works for their own project and formulations, right? But still, you want to see it, you want to check it, you want to make sure that if the mix has a little bit more water that you don't like, you need to tell that concrete producer that you don't like it because all of a sudden you don't like it. But what you don't know is that the concrete producer may tell you, Mr. Engineer, that material I'm using actually has a certain water demand that I need, and I need to maintain that water at a certain level. However, I'm using some admixtures here to compensate for that performance, and I'm going to give you that performance, which is the approach used in Mexico and Canada. They work with the concrete producer, they work with the engineer, with the client, to have a mixed solution that actually doesn't need to provide the formulations. They just work on performance and calibrate towards that performance, okay? Now we're going to talk about the slump. Sorry. So with the slump goes a similar conversation. What is a slump? Why do you need slump, right? What does a slump means to the design performance in service? So I'm showing you here some things to start thinking about, because if you are one of those that think that 4-inch slump is the best concrete that you can get, as we know many people think, then I'm going to start knowing how you're going to do that for that type of rebar that I have there. Because it's easy to put research and it's easy to talk about bridges that are in simple communities and municipal areas that don't have a lot of that rebar, but think about how I'm going to do that one. How are you going to do that rebar congestion and build it right, consolidate it, have good quality, avoid cracking with 4-inch? Because you say that your research say 4-inch concrete is the best concrete you can get, right? That's a problem we have in the industry in the United States. Sometimes the research is not relevant to the standards. We adopt it in the standards, and we keep moving with the standards, believing that we have the right performance. That can be problematic. So I show you here different levels of slump. All of them are good quality concrete. All of them have good durability. And I'm going to ask you a question. Which one you think is a higher strength or better durability in those 3 photos? Because I believe we have a lot of experts. So I believe by looking at slump, you know which one is the right one. He could be saying, what do you guys think? The SCC, he's saying. He's selling on mixers, so I cannot say anything there. You know what I mean? What do you think? Anybody else? Which one is better there? Better strength, better durability? More cohesive, okay. So the funny thing to Doug and the same mix the same mix was targeted at different consistencies of a slump. It's exactly the same mix, the same aggregate proportions, the same materials, the same water cement ratio, with admixtures adjusted to make it from a 6-inch or 7-inch to a slump flow. Exactly the same. And that's why the misconception of people about, obviously, the slump. You can make the same thing look different. If you have the right proportions, you can make it look different. Okay. So then the other part about construction is obviously, we keep talking about slump, but what does that mean, right? We have here an operation that requires a certain slump retention. So it's also how you're going to build work. You need a slump to construct it, but you also need to target a certain slump retention to build it, because construction demands vary. So it's important to understand that. So, okay. So we got to the comparison of the standards. And ACI 301 obviously established, they have obviously modified their approach, and they have checked, target slump at the point of delivery needs to be specified, and the target slump shall not be greater than 9 inches. And there's another section for slump flow. So they allow also that. In Canada, they talk about the slump requirements shall be identified and reviewed by the contractor and concrete supplier prior to construction. So like I mentioned, in Canada, they believe and trust. The culture has the belief and trust that the different parties have the responsibilities to meet. And if the concrete producer and contractor decide to have a certain slump, they go with that slump. Okay? So there's the culture to build on that thought. And in Mexico, when you look at the standard, it talks about you have a certain slump that you target for purpose of water content, but after that, pretty much you have mixtures to develop the target slump. Similar to Canada, where you actually have the freedom of the concrete producer with the contractor to establish a slump. However, in the U.S., we like to put a limit to everything. 4-inch or 6-inch, it doesn't matter what you're going to do, you need to deal with it, right? A challenge. We need to work on that challenge. Mass concrete, I'm going to talk about mass concrete because it's another topic that we have a lot of different opinions in ACI and CSA. Although the concepts are recognized in ACI, in CSA we have been able to move faster, to adopt them, to integrate better knowledge with practice. And important to recognize mass concrete, traditional mass concrete, think about it more like hydro dams, you know, the big work that doesn't have a lot of reinforcement, they use larger rocks. When you think more about thermally controlled concrete, it's going to be more the structural, isolated, large, you know, placements that occur in bridges or buildings, okay? So the first thing about defining mass concrete, in ACI we recognize that, and this is on a non-mandatory section, but we recognize that about, you know, 4 feet or greater, pretty much you start getting to mass concrete. In CSA, you actually get into also about 1 meter, which is 3.28. If you want to kind of make it into feet. So you between 328, 4 feet, so kind of saying about the same numbers. And then also now in ACI we have guidance for defining mass concrete, which relates to the type of mix to the size of the element. So it's pretty much a correlation of how much heat we expect can be generated in certain placement based on the amount of heat you have from the cements, from cementitious materials to the size of the section. So as you can see there, you're likely going to be around the same target, 3 to 4 feet, pretty much is in between Canada and the US, where you're going to be starting to define mass concrete. It's not an easy number to define, but certainly somewhere there. And then what we did, we have been doing, and we had actually a meeting about this today, in ACI, we're not planning to change the temperature limits. We have been going over the last 2 cycles in ACI, discussing the concepts we implemented in CSA in Canada. We have decided to do not make a change on that. We continue to have 60 and 35 degree differential. So 160 in this case is the maximum temperature. However, it's recognizing the approach that we took in Canada, which is using supplementary cementitious materials to optimize the temperature profiles that you can get and make sure that you manage thermal controls. In CSA, we have a different approach, which is this one, and it actually recognizes what we already have in ACI as a guidance, but now we recognize it as part of the standard. We're pretty much saying, if you don't have any mitigation with supplementary cementitious materials, you do not exceed the 70 degree. However, if you have an improved system that has cementitious materials at certain levels, right, so as you increase them, it's different levels, then you get into allowance of 75 degrees up to 85 degrees, okay? So pretty much you can actually have a determination of performance. What is the type of application you have? What is the type of size of an element you have? You may have a large size element that you may need to put more powder, and you actually can tolerate more heat because you improve the chemistry of that cementitious combination. Then you have the same concept for differential. 35 is a fixed limit. We have it in the US, in ACI. We also recognize in the paragraph below that you can go and use a design approach to actually calibrate a performance-based temperature differential. However, when you go to Canada, we already adopted the concepts of performance, and they're part of the standard. So on the top, you have the differential of 20 degrees, which is 35 degrees Fahrenheit, and those are established in ACI 2 as the default standard. However, we directly now recognize in Canada that you have different ways of doing this. By recognizing the development of concrete properties and qualifying them, you can actually have higher temperature differential, okay? How does that look? So when you look at the fixed limit, that's a concept that is traditional standards. Traditional 35 degree, even if you go to higher temperature limits, it's just fixed. It doesn't recognize performance. It doesn't recognize that concrete gets better with time. It doesn't recognize that your strength is going to be better at 7 days and 14 days and 3 days, okay? By looking at performance, then you can create an approach that actually recognizes the ability of the concrete to improve. And that's what you're doing with the concepts implementing performance. These are qualified, calibrated with analysis and testing, and you're able to determine something like this. So if you look at an example, just directly an example to like an ACI limit of 35 degrees, you can see where it is in this case. You see the opportunity we're losing and the inefficiencies that we have in construction by just limiting a number. Because all of a sudden, you look at the 35, it doesn't change with time. But then look at the curve on top, and that's the mix. You had a mix that have a very good tolerance to tensile, strains from heat, right? From the differential of the heat gains and loss of heat, right? So you get a thermal strain occurring, but the mix is actually generating enough tensile strength to actually tolerate those tensile strains. So what you're doing is you're increasing the capacity of that mix with time, then now you can tolerate a higher temperature differential as the concrete gets stronger. What happens with that? You can build concrete faster. You can be more efficient. You can avoid a lot of the cooling that occurs that actually takes a lot of energy too, and be able to actually produce a high quality product without having to be constrained by prescriptive numbers. Because these are prescriptive numbers. They don't even have a technical basis for it. Okay? So that's the concept that we implemented in Canada. As you can see, very good opportunity for improving performance of work. In Canada we do it. In USA we talk about it. We don't want to make a decision about it. We are afraid of it. Don't know why, but we continue to be afraid of understanding concrete. And then the next one is durability. So when we talk about durability, durability is actually important for concrete. You can imagine that there's nothing better than to make concrete sustainable, to be durable. And I always say, what is the most important part of concrete to be durable? It needs to be workable. Because if you cannot place it and you cannot finish it and consolidate it, then you cannot do, you cannot have anything to do in the field. It can be good in the lab, but you cannot do it in the field, right? So, meeting the concrete properties is important, avoiding degradation mechanisms, and improving resistance to corrosion. Okay? So let's talk a little bit about that. Okay? So what are the concepts that we typically have available? Think about a concept we have available to make those decisions. You can provide better cover, you can provide better concrete, you can improve the rebar, and you can provide the ability of anything to get into that concrete. With coatings, right? Surface treatments. Okay? If you look at the first part, cover, it's well addressed, but pretty much every code, every requirement, right? You need to have a certain cover. And then you have water-cement ratio. Okay? All the other parts that you see there, if you look at ACI codes, it's not addressed. All you say is that to be on C2, okay, which I'm going to show in a minute, when you're in C2, you need to have a maximum water-cement ratio and a minimum strength. And all of a sudden, that's it. That's the solution to make concrete durable. That's it. Do you see anything else there? Do you see any performance criteria testing? Do you see any correlation of performance with materials that can improve that material property of durability? There's nothing. This is the current ACI 318 standard requirements. Nothing. Okay, so if somebody tells you ever that you have good quality concrete in the bridge because they meet the code, good luck. Get out of that bridge. Honestly. Right? But now look at how Canada and Mexico are doing things different. These are our neighbors, right? So North America, our neighbors. So the first thing, and I'm not going to get too much in the details because I know Doug is going to get into all the details, but we have all these different classifications of exposures, right? And I'm going to focus on just, these two. When you see those two, right, and you want to think about, what C2 was in 318, but put a little bit more levels of effort and requirements to understand performance. Well, that's what Canada did, right? Canada pretty much took these minimum requirements and just used a performance criteria to supplement the ability to have better durability and performance in service, okay? Now, we have also in Mexico different series of requirements, and these are just a classification of exposures. We have 3 pages of classification of exposures in Mexico. And I know everybody has seen the 318 in Spanish and 318 in English. It's always longer in Spanish. Okay? I guarantee you that. I cannot guarantee you what's going to happen, but the 318 in Spanish is always going to be longer. And that's why I don't write anything else in Spanish. I do it in English. Okay? Don't ask me to write in Spanish. It's going to be a long report. But anyhow, this is in English, but it's just the culture, right? We like to explain things. We have a lot of passion and energy, but we like to explain things. We like to say things 3 times to see which one you laugh. And you laugh at one, that's a good, he got it. The other 2, he didn't get them. But anyway, the point here is look at this. I love this table, by the way. And we're doing a lot of work in Mexico, and I'm glad that they're doing what they're doing. It's a very well thought table. They got from erosion resistant to sulfur resistant to all other durability mechanisms. And you see that yellow line that I have there? There's a permeability criteria associated to these environments that are, for severe exposures. We go back, guys, we go back. We go back to 318. We look at what we got here. It's a bare minimum. We just say with water-cement ratio, we make the world better. But Canada and Mexico are doing performance testing for this. Okay? So this is extremely important lesson learned here. We need to start thinking a little bit more about durability and performance. We're working on a code. All that is going on the works. But as you start thinking about why we're doing all the efforts we're doing with developing codes and developing standards, This is extremely important for the U.S. So then I'm closing here. I have a couple more slides closing. But this is something extremely important. These are projects that we have done. And this is more of a mindset. I started with perspective of concrete, this mindset. This is the first project I'm showing here. There's two projects actually. That's the Inglewood Stadium. And the bottom one is a Fast Fix 8. Those are accelerated fast track projects we did. Extremely successful projects, okay? And these two are emergency projects, okay? Everybody remember Katrina? The fatal event in the United States? We reconstructed all the levees and all the emergency structures for New Orleans, okay? And then we also did the emergency project in Spillway in Oroville Dam, okay? When the dam collapsed, obviously the spillway collapsed, then we went there and did the work. I'm going to tell you there's one trait, just one, that is common in those four projects. Commitment to excellence. Because there's no chance for failure. We don't have years to build something. We don't have the ability to take 4 weeks review process. Everybody from the design, the owner, the contractor, the producers had one goal. You need to get it done. I need to get it right. But when we are not in a schedule that is accelerated, when we're not in an emergency, all of a sudden we become dumb and lazy. Right? But if we put our thoughts and we work on commitment to excellence, like we do when we got it under pressure, all of a sudden we are amazing. So when you look at the problems we have in the industry for standardization, it's not ACI, it's not US, it's not Mexico, it's us as people that are not willing to actually commit to achieve excellence, right? Basic things like SMART. We all learn these in management. We all learn these in the basics of setting a goal. We go to develop spec, we don't know where to start. This is all basic stuff. Specific, measurable, achievable, relevant, time-bound. That's going to get you to be constructible and be high quality, right? And then pretty much, just to sum it up, we need to have requirements that are technically sound, relevant to work, specific, aligned with demands of the work, achievable, executable, performance-driven, because we need to make sure we perform, and flexible to fit the different purposes, and there's no one-size-fits-all. So because the left side here have a solution and the right side have a different solution, doesn't mean that one is right or wrong. Just different solutions. Well, hopefully you understand the goal of my presentation today. We're sharing the approach to the different standards in North America, and we have a couple of minutes here, I think, to ask some questions, right? The materials. You're saying like the cementitious material? The manufacturing of cements is what you're talking about, for example. So I avoided getting to that discussion. I believe Doug is going to get a little bit more in that in the Canadian side. But I can tell you this from experience. The recognition of different types of cements, going from performance to blended to hydraulic cements, between Canada and Mexico and the U.S. Canada and Mexico, they adopt cementitious materials that are different than just a traditional general use cement much faster than we do in the United States. We're struggling right now with Portland limestone cements. They have been having that for a long time. And if you look at the type of cements they have, sulfur resistance, blended with slag, blended with fly ash, they use them everywhere without problems. When you try to bring one of those to any of your local communities in the United States, you spend months and months and months adopting. So we have an issue. The USA is very prescriptive and limits the ability to use new technology and new emerging materials. It takes longer here. Let's put it that way. They are adopting faster, they're using it, they're having success, but all of a sudden we that are in the middle have a magic issue that we don't know what it is that needs to be resolved. But certainly performance in Canada and Mexico is moving faster than in the US. Good. Well, thank you very much.